I'm Camille Chesley, a reference librarian here at the University Libraries, and today I'm introducing our speaker, Dr. Yanna Liang. Dr. Liang is the founding chair of UAlbany's Department of Environmental and Sustainable Engineering. Her talk today is entitled The Pursuit of Sustainability. Dr. Liang received her Bachelor of Engineering in Environmental Engineering from Suzhou University of Science and Technology and her master's and PhD degrees from Utah State. Before Dr. Liang started her academic career, she worked for the EPA both in China and the United States for more than 8 years. Her research interests include the fate and transport of engineered nanoparticles in aqueous and soil environments, water and wastewater management, and solving environmental concerns using biological processes. Please join me in welcoming Dr. Liang.
Thank you so much for the introduction, and thank you everyone for coming to this talk. Now, this talk is called Conversation, right? Conversation is not just, I'm assuming it's not just me talking here. Oh, do I need to? Okay, thank you. So when Camille asked me for the title of the talk, I didn't hesitate to just say, wow, this one you see on the screen. But then last week when I started to prepare for the presentation, I thought, wow, this is such a big topic. Where should I start? So last Wednesday, I sent an email to my colleagues and students in the College of Engineering and Applied Sciences. So I asked them several questions. The first one is, when you hear the term of sustainability, what comes to your mind immediately? So I asked them, just give me 1 or 2 words or 1 or 2 phrases, just to let me know your immediate response, because sustainability is not a new word. So some people did send me 1 or 2 words, and then if you don't have this immediate response, please just explain a little bit. For example, how can we accomplish sustainability, or what in the society so far you think is not sustainable, or what are the approaches we can use to achieve sustainability. So I got very, very nice responses from my colleagues. And so basically, I'm an engineer, so I'm just presenting this using graph. Most of the concerns are related to natural resources. So the concerns are we are using lots of resources, but again, these are limited. And then the waste. We generate lots of waste. How can we handle all of this waste? And then the energy, and then the 3 R's, reduce, reuse, recycle, and then the environment, carbon footprint, global warming, pollution prevention, all of this. So there are different but broad perspectives. Okay. So what is exactly sustainable development? Again, you may have heard about different definitions from different talks, textbooks. So this is a very, very old definition given by UN. It says development that meets the needs of the present or the current, but not compromise the ability of the future for future generations to meet their own needs. Okay, so this is a very basic definition. I like it because it's catch the essence of sustainable development. So here talk about needs, and then I'm an engineer. So National Academy of Engineering identified 14 grand challenges for engineering in the 21st century. And then the 12 grand challenges are grouped into 4 cross-cutting themes. Number 1 is sustainability, and then there is health, security, and joy of living. So they are all interrelated. You cannot just talk one theme without mentioning or thinking about the others. So again, here the term here, sustainability. So what do we need? So here I'm just listing, as a regular person, what we need in our daily life. So first we need a place to live, okay? So this is a nice house. What do we bring to the house? So we need water, we need food, we need clothes, we need furniture, we need power, electricity, and we need gas to fill the car. So this is what we need, we bring to the house. But what give back to nature? So after you use all of these resources, what we give back to the environment? We give all the waste, right? So there's wastewater, there's solid waste. Now, solid waste you are most likely aware because you put your garbage outside, right, for pickup every week. Now, wastewater is something probably you're not so aware about. Because wastewater, you use water, and all of these dirty wastewater is being discharged, released through pipes, right? Pipelines and go to somewhere. So probably you don't think about wastewater that much. So if you look at this slide, what else do you need in order to live here on the earth? Not emotional, not spiritual, just material needs. So besides what, very good, yeah. We also need air, right? So air is everywhere, so I didn't add air on the slide. We cannot live without air for sure. Thank you. So talking about air, I'm going to talk about atmosphere first. Because right now we have this urgent issue of global warming and climate change. So this is CO2 concentration. Again, it dates back to 800,000 BCE to 1950. And then from 1950 to right now we are here, 2018. So you can see there's a huge jump, and then the jump happens after 1950. So this is CO2 concentration increasing in the air over the time. And then methane, CH4, so this is a major component of natural gas, and this is even worse chemical related to global warming, greenhouse gas. So again, you can see the similar trend dramatically increased after 1950. So this is recently reported by IPCC. This is Intergovernmental Panel on Climate Change. Now, before this report was published, we all talk about the 2 degrees C scenario. So if the global temperature increased 2 degrees C, and we expected the consequences would be dramatic and huge. Now we are moving from 2 degrees C to 1.5 degrees C. So that means this matter is even more urgent and critical. So this conclusion of 1.5 degrees C is based on this analysis. On the top graph shows impacts and risks associated with reasons for concern, the RFCs. So there are 5 RFCs, and then the darker the color means the risk and impact is more, the risk is higher. Okay? For example, the first one, unique and threatened systems. 1.5 degrees C is over here. If we reach 2 degrees C, then the risk is just too high. Now the second one is to either natural, managed, or human systems. And again, the first one, the warm water coral reefs, they could be affected very, very bad. Now, I would prefer 1 degree C. This is already very, very high. 1.5 is here, it's like purple color. So that means the impact could be severe, So all of this is based on the measurement that we have. So here we have the measurement from 1960 to 2017. So this is CO2 concentration relative to this time, and then how it varies in different years. And then here is a projection made by IPCC and different scenarios and how we should end up with 1.5. So here, it's a very busy slide. I don't have to read it, but the take-home message is by around 2050, we have to reach a point where the net CO2 emission is 0. So what is net CO2 emission? So if you look at the CO2 or the carbon cycle, there is CO2 emission. So you have CO2, carbon goes to the air, and then you also have CO2 precipitating water, and you also have CO2 utilization by plants through photosynthesis. So it is a cycle, but overall we have to achieve a net CO2 emission 0. And that is a very, I would say, very, very severe task to achieve. It's not easy. It's a grand task we have to think about. So that is global warming. So we do have that reality to face, but how can we mitigate the effect? So number one, like I just mentioned, reduce CO2 emission, and these are the areas or topics floating in the scientific community. Number one is, can we reduce the sunshine, basically, or can we reflect the sunlight back to the space to decrease the temperature? Okay, so that is called atmospheric interventions. And number two is basically, can we just suck the carbon out of atmosphere? So imagine you have this huge vacuum, whatever, you can just suck CO2 out of the air. Easy to say, but definitely not easy to do because atmosphere is just so abundant, it's just so huge, right? So these are the big ideas. So now I'm going to talk about air quality instead of this atmosphere, global warming. In terms of air quality, if you care about the air quality of where you live, so EPA has this very nice programs called Air Now. So you can go to the website and then you can find out the air quality and also for different parameters. So here's ozone, particulate matter, PM 2.5, PM 10. So this is the map I put up yesterday at 5 p.m. The green color means it's good. So you can see the legend over here. Green means good, and the yellow means moderate. So overall air quality is okay. But we do have several pockets that are yellow. That means for some very sensitive population, the air quality probably can be improved further. Okay. So this ambient, outside air quality. Nowadays we pay more attention to indoor air quality. People used to think indoor air quality is good, but if you take a closer look, probably we have to be serious about indoor air quality. And again, so EPA has this website. I guess I have to click it. So this is the website you can go to. So it has the analysis. Oh, well, okay, so I don't have that flash. Okay, just give it. So if you go to the website, you can click each room, bedroom, living room, kitchen, and basement. It will show you what kind of concerns you should be worried about. So there's chemical exposure, volatile organic carbons could be emitted from some chemicals you use. And then what EPA did not or does not mention in that, I would say, interactive map or video is chemicals that could possibly be emitted from carpet, for example, carpet or couch. Now, nowadays, the carpets are advertised as stain resistant. I mean, that's good, right? That is convenient for consumers. If you spill something on the carpet, it wouldn't cause a stain, so that is good. But think about, the carpet are made from fabrics. If it is stain resistant, how can that be? So there must be something added to the carpet or added to the couch to make it have that function. So the question is, are these chemicals safe? Do they cause any danger or risk to people who use them? So that's something we as environmental engineers we want to figure out the indoor air quality, how much is affected by the presence of these potential chemicals. Water treatment. So back to the slide I showed you in your house, you bring water into the house. So how do you get your water? Please?
Yeah, they take water out of the river, what have you, or sewage treatment plants, and then treat it to send it back to you. Maybe. Well, or the water comes from heaven.
Okay. Okay, so water comes from the heaven, goes to the rivers and lakes and reservoirs, right? Okay, very good. Any other thoughts? So, do you get water directly from these places?
No.
Not directly?
Wow.
From a well? Can you drink water directly from the well? No.
You can.
You can? Used to, right?
Saratoga-
I mean, in the old days,
Saratoga
people just drink
Springs,
water
you
directly
can.
from the well. So here's the video. Hopefully the video will work.
How does drinking water get to your home?
Wow. I'm not really sure. Probably through a series of pipes.
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 Pipes and what?
Through pipes.
I have no clue.
I assume it comes up through the pump in the ground?
Through a filter?
Gets to a house with a pump, water pump.
nature. So beautiful and calm.
Hey, Splash, did you know that reservoirs like this are one of the places where we get our drinking water?
Wait a minute there. You don't want to drink this stuff. I'm telling you, I've been in a lot of water, including this reservoir. You know what's in there? Fish. You know what they do, right? They
Oh, Splash, don't even go there.
You know, a lot happens to this water before we can drink it.
You're telling me? Hey, I've been cleaned up a few times.
New Jersey American Water's experts work round the clock, removing bacteria, viruses, micropollutants, and other harmful particles from the water you drink. They do such a good job that American Water often provides water service that is better than what the government requires.
The treatment process begins here, at the pumping station.
Pumps draw raw water from reservoirs, lakes, rivers, streams, wells, or underground aquifers. Water travels by pipeline from the pumping station to the treatment facility. The first step in the cleaning process removes sediment and particles from the water with the help of coagulants.
What?
Coagulants are chemicals that act like magnets. They cause particles in the water to stick together. These groups of particles are called floc.
Huh, I didn't know I had it in me.
American Water uses two common processes to separate and remove floc from water. One sinks floc to the bottom of a tank. The other method pumps air into the water and floc, causing residual particles to float to the top. The separation of water and floc is called clarification. With either method, the clarification process removes most of the floc from the water. The next step, filtration.
Whoa! Hey, watch it! Wow, can a water droplet get a bruise? Sheesh! Ow! Wow, I just got pushed through layers of activated carbon, sand, and gravel. Please tell me I'm clean.
Sorry, Splash, you're not completely out of the water. You're filtered, but you might be infected with tiny microorganisms. Don't worry, disinfection doesn't hurt. Chlorine and ozone are just two of the ways we disinfect water at New Jersey American Water.
I love chlorine. It's been disinfecting water and keeping me clean for over a century. But what's ozone?
Ozone is supercharged oxygen. These bubbles scrub and disinfect. Viruses, germs, and fungi don't stand a chance.
Whoa, hey, that tickles! Stop it already! I'm gonna wet my pants!
Hey, Splash, guess what? You're finally drinking water, ready for distribution to homes and businesses.
Are you sure? How do you know?
New Jersey American Water's certified operators and water quality specialists test and monitor water throughout the treatment process, from source to tap. In fact, we conduct thousands of tests on your drinking water.
I'm certified, verified, decontaminized, and feeling fine.
Okay, so Splash says he is decontaminized, certified, verified, and clean. Is it really clean? The water you drink is truly 100% clean? Yeah, so it depends on the pipes, and then there are other things I'll talk about later, so we have to think about and see, okay. But anyway, so you can tell the water treatment process is not like a one step. So it involves multiple steps. It's a physical chemical process. You add different chemicals to achieve different purposes. So hopefully you start with, for example, liquid water is turbid, and then you comes out with something free of particles, free of microbes. So that is relatively, I would say, safe to drink. Okay? So relatively, not absolutely. So that is a water treatment. Most of people use water from water treatment plants, and then some people use water from wells, private wells. They just do a very, very simple treatment process. Then the water should be good to use. Now the second one is wastewater. Like I said, from the house we release wastewater. So how wastewater is being treated? It's a very, very messy process. I would tell very, very messy, much messier than the water treatment. But But again, this is lunchtime, and we would behind. I'm not going to talk about, I have the videos here, but I don't want to show you the videos to upset you, tell me. So just give you some information. So this is a map of wastewater treatment plants. So each dot here represents one plant. And so there's small dots, big dot, that is related to the flow rate of the treatment plant. For the big ones, for example, the one in Chicago, that is a million gallons per day, very, very big. And for small communities, you have a very, very small flow rate. But anyway, so that is the distribution. Now, the typical process for water treatment involves, commonly speaking, 3 stages. Number 1 is called primary, and then followed by secondary, and then sometimes you see tertiary, also called advanced treatment processes. So we have wastewater go in, we use a screen to get rid of the big stuff, chunky stuff, and then use grit chamber to remove sand, to grab small silt stuff, and then we have this clarification or sedimentation process, and then we use secondaries, aeration plus clarification. So that is a key step in wastewater treatment. So this is a very conventional design for treating wastewater. Nowadays, we are adding the tertiary step. So basically, you can use sorption, you can use filtration, especially using membranes. So you can get water that is suitable for drinking. So back to you, you have sewage. After treatment, the water is good for drinking. But that is a very, very extensive process. So the questions to you, like I asked the first one already, is drinking water from the water treatment plant safe enough, clean enough for you to drink? Now the second question is, will the treated wastewater do no harm to the receiving environment? So for wastewater treatment plants, it receives water continuously. So your wastewater flow to the plant 24 hours, 24/7 basically, and then so water is treated, then it's released to the environment again continuously. So most likely it will be released to rivers or lakes or reservoirs. So will the treated wastewater good or not, at least not cause negative effect to the receiving environment? So then that's something we have to think about. So these are the problems related to, I say, this traditional or conventional water wastewater treatment. Number 1, time. Do you know when EPA was created? Or when was EPA created? No?
70s?
Yeah, 1970. So EPA was created in 1970, and following that, a lot of water wastewater treatment plants were built in the 1970s, in the 1980s. How far from now? 40 years, 50 years. So these plants, they are very, very close, or either some of them past their design life. So it is old, it is old. And another factor is they are designed to meet EPA requirement. If EPA says, your water, the effluent has to meet this criteria, then the plant can do that. But this requirement or these regulations has been for so many years, ongoing for so many years. Are they suitable for nowadays? Probably not. So this is the estimate using $2012. So we need approximately $271 billion for the whole U.S. to upgrade or repair the existing treatment plants. So it's a huge amount of money. And then different states have different requirements. You see the 2 dark blue colors, New York and California, they need the most among all the states. And then specifically for New York, per person, New York is also among the top. So we need a lot of investment to improve our existing infrastructure for water wastewater treatment. So fortunately, we have this Clean Water Infrastructure Act that passed last year, 2017. So that provides $2.5 billion for this purpose, water quality improvement, protection, which is good. But still, there's another problem is the current plants are not designed to handle emerging contaminants. Okay, so what are the emerging contaminants? So these contaminants also called contaminants of emerging concerns, ECEs. For example, pharmaceutical compounds. So people take lots of drugs, and then all of these drug companies, they synthesize, develop new drugs every day, right? And it's good for people's health. But again, after drugs are being taken, metabolized in the bodies will be released to the environment. Okay, so that's pharmaceuticals. And also we have these endocrine disrupting compounds, so they're hormones related. And we have personal care products like shampoo, lotion, sunscreen, deodorant, all of this. And nanomaterials, and also the per or polyfluorinated substances, PFAS. Okay. Now one example is approximately 256 personal care products contain either nano or micro-sized ingredients. So what is nano? Nano means these materials has nanometer size. Nanometer. So you start with meter. 1 meter is 1,000 millimeter. 1 millimeter is 1,000 micrometer. 1 micrometer is 1,000 nanometer. So think about how small these particles are. And if you release them to the environment, what kind of impact they can cause. So we use lots of nanomaterials. For example, here it shows active ingredients in the sunscreen is titanium dioxide and zinc oxide. So these are active ingredients. But here it specifically illustrates is non-nano. So the materials, the particles are not nanometer size. But in other sunscreens will show this is nano zinc oxide. Okay. So these small particles, they are so small, but they're so powerful. Because they are small, they have huge surface area. So they are very reactive, and they are very, very, I would say, active. So because they are so small, they can penetrate into even the smallest microbes, but they are smaller than microbes. So in the environment, what is the impact? We just don't know too much. So here this goes a little bit of my research about impact of nanoparticles to the environment. Now 10 or 20 years ago, when people are concerned about the impact of nanoparticles, they studied the nanoparticles at very, very high concentration. So in the environment, the estimated concentration is around like microgram per liter, so that is ppb. But in the labs, people study gram per liter, milligram per liter, thousands or millions of higher concentration, and then they study only single or individual microbes. For example, just E. coli, or just the baker's yeast, Saccharomyces cerevisiae. But you don't see this in the environment. You don't see that high concentration. You don't see only single nanoparticle in the environment. So you have tons of results published in the literature, but how useful they are, I'm just not convinced they can be applied directly to the real world. So what we did is we took samples from a river. So what we get is a microbial community. So basically you have lots of microbes in the water, and we expose them to low concentration of mixed nanoparticles, and we see the effect. So here the blue bar is control, which means there's no nanoparticles. So this is this dominant proteobacterial phylum, and then this is exposed to titanium and zinc, so there's decreased presence of this phylum. And then with the additional silver nanoparticles, the effect is even more, okay? So this is so definitely you can tell there's impact. We also look at the species distribution. Again, the different color means the different distribution, composition. Again, there is impact. And so here shows clearly, so we have the controls, they are here, and then all of the treatment with exposure to nanoparticles are separate from the controls. So the analogy is like, in the community we have dominant species. Now once the community is exposed to nanoparticles, for some unknown reasons, the dominant species are decreased or knocked down. So once the dominant species are decreased, somehow the minor species came to be relatively equal. So kind of like in a class, you have a bully. Once that bully is out, all of the little kids are happy. So we don't know why it caused that, but that is what we observed. Next topic is PFAS. Like I said, the poly and perfluorinated substances, they belong to emerging contaminants. So if you have heard about the incidents at Hoosick Falls or maybe some other communities, Petersburg or Newburgh, I think. So you should be aware of these two names of the chemicals, PFOA, PFOS. So this is what we hear most often. But again, these two, if you go from bottom to top, it's like still in labs. Okay, it's only sorption. But is sorption good enough? So to use sorption, you have to start with a sorbent, a material. Okay, so how to get sorbent? Activated carbon here has been used broadly, and then so you can get AC from these materials. For example, you can get from nutshells, from coal, from wood, and you can do choose one of the two, either physical or chemical. So for physical, you do carbonization, followed by activation, or chemical, you can use acid base, or followed by activation, you get activated carbon, and then you can do the AC filtration, you get filtrate, which is PFAS free, and you have spent sorbent, and you have to burn or incinerate the spent material at over 1,000 degrees C. So the process works. I mean, so far this is the most effective process that can be used at water treatment plant, for example. But if you look at the whole process, it is fairly expensive and also very energy intensive. Okay. So what we do in our lab, number one, we try to use nano catalysts, and these catalysts are photoactive to degrade these chemicals. So if you look closer, that's how the reaction takes place, and then the final product is CO2 and fluoride. And we're also working on using a green practical process to uptake PFAS from water, and then we do the conversion process. So I won't go into the details now. So in the process, I studied these emerging contaminants, nanomaterials, and the PFAS. So this is a question I ask myself many times. Have we learned our lessons yet? If you look at the history of environmental protection, there are so many incidences or case studies. We can learn some lessons. So, for example, in 1962, there is a book published by Rachel Carson, Silent Spring, so that describes the chemical DDT, the pesticide. And in 1980, we have this nonfiction book, Civil Action, and then that was made to a movie later. So that is about the chemical PCE, this organic solvent. And recently we have this lead contamination, Michigan. And then several nights ago I read this. This is a study published by NIH, and it says rats exposed to the 2G and 3G radiation, basically iPhones, had higher tendency of developing tumors or cancers. But again, NIH cautioned, these are rats, not human beings. And again, the radiation, I think the dosage was higher than what we encounter daily. But again, you get the message. So it's just that we have so many case studies, and we have so many, I'm not saying accident, it's just we are still dealing with this cycle at it again. We haven't learned much. It's like every day, every time we have these amazing chemicals come to the market, everybody just grabs and use it without considering the potential consequences of using them. Now I'll go back to solid waste. So here's a saying I like very much. It said waste is not a waste until it is wasted. Okay. So if you look at your daily life, we probably just generate like two kinds of waste: electronic waste, computers, iPhones, iPads, and organic waste. So if you look outside, we have leaves everywhere, so that is one type of organic waste. Again, so this is yard trimmings or agricultural residues, or you can have, so this is biosolid. You probably don't know too much about biosolid, but it's okay. And we have kitchen waste. So the question is, can we convert this waste or recover something useful, valuable from the waste materials? So my answer is we have to. So nowadays, probably you are not aware that we use lots of products. So here is a finished product and consumer goods. For example, carpets, films. You go to here, tires, and even there is pens, pencils, plastics. We use lots of these products in our daily life, but they are made from fossil fuels, from petroleum and from coal. Okay. But again, this is after extensive process, from this raw material to commodity chemicals, secondary chemicals, intermediates, and we make these final products. So we use a lot of indirectly for the fossil fuels. So some people will say, I don't want to use any fossil fuels, which is good, But again, the fossil fuels are not just used to make fuels, gasoline, jet fuel, diesels. We use so many things. Look at the room. You just don't realize they are actually for fossil fuels. Now, if we stop using fossil fuels, then how or where we can get these products we are using daily, we have been using daily. So here's the option. We could still get all of these products for biomass feedstocks. Biomass feedstocks, in other words, basically is plants, trees, agricultural residues, all of this, or you can say those from organic waste. So we can break down to different components, and again, we go through these different processes, we can produce this product. So if one day, we don't have fossil fuels, petroleum, coal left, we can still survive. But again, we have to get all of this we need from this, I would say, green material, which is better. Now, technically, we can do this already. We can do this conversion. Technically, we have this feasibility, but again, economically, it is still much more expensive compared to make products from petroleum or fossil fuels. The last topic is energy. So I'll go fast, so some people are kind of tired. So energy production in 2017, as you can tell from here, the majority is natural gas, followed by crude oil. And then the consumption is in 2017, we consumed 37% our energy from petroleum. So again, it's dominated by fossil fuels, petroleum, natural gas. Renewable is only like 11%. So this is how this energy are being used by different sectors, different sources. So petroleum, 72% goes to transportation, and for transportation, I think that is 92% is for petroleum. Over time, from 1950 to 2017, so the use of coal has been decreasing, natural gas increasing. If you look at the renewables, there is a big increase, but recent years not too much. Breakdown of renewables, hydroelectric is the majority. If you look from the top, this is solar, just tiny part. Wind is pretty good. And then we have geothermal biomass. New York energy consumption 2016 is pretty good. So this is from high to low. New York is per person is 185 million BTU per person. That is ranked number 50, so that is pretty good in terms of energy consumption. And the majority, again, is from natural gas and some from nuclear power and also from hydro. CO2 emission not so good, so it ranked at number 9, so basically the 9th highest in the nation. Now wind. Wind is good, so it is renewable, it is sustainable. Again, basically it is everywhere, it is vast, but the disadvantage is you have to install this wind turbine, this huge, gigantic structure you have to invest at the beginning, and that is not cheap. And again, no location, you have continuous wind, okay? And also the power is variable, and also the damage that could be caused by strong wind. And we install this, the wind turbines are very, very tall. That's because at a higher place, higher elevation, the wind speed is higher compared to the surface. So there are 5 regions in the US. The majority is from interior region here, and then northeast is just a tiny fraction of the overall. And here you can see the individual state, and Texas is number 1 in terms of the capacity of wind power. So onshore wind energy compared to other countries, so among 23 countries, US is over here, still lagging behind some European countries. And offshore, you can have these wind turbines in the sea. Offshore, again, US is only 0.2%. Way behind UK and Germany and some other countries. Now solar. Solar, again, is not a new concept, PV cells. So this effect, photovoltaic effect, so basically photon is element of light. Voltaic means voltage, so you have photon generate voltage, electricity is called PV. So that was discovered in 1839, and then in 1954 we had the first PV cells developed, and then similar time frame it was used in very, very remote places or used in satellite. Advantage again, it is clean and renewable, and then compared to wind, there's no noise. So if you talk to people who live very close to the wind farms, some people complain the noise. So the noise is like low frequency, but it's constant, always there. So, but solar, we don't have this issue. And also the maintenance could be low, and it's free after it is installed. Drawbacks, again, not cheap at the beginning, and also location dependent. And different from wind, we don't have light at nighttime, right? So the energy is intermittent. We have to store the energy in some ways. So right now, the battery research is it's a big topic. The price of solar has been decreasing dramatically. So the dashed line here is a price drop, and then the solid line is a production. So correspondingly, the production has been increasing dramatically. And then this is a projected cost by U.S. Department of Energy. So there are 3 sections: residential, commercial, and utility. And in 2017, we are here 16 cents per kilowatt hour. And you can compare with what you pay for your electricity, what you use for your home. I think I checked last night, national grid is 6 cents per kilowatt hour. So here for residential, solar is 16 cents. And this is worldwide, and again, 2010 dominated by Germany, and then 2013, so China here caught up 13%, but still US is not a major player in solar. EIA forecast, so consistent with the figures we saw the last slide, India and China, they're going to increase their capacity dramatically. And so this is for residential, there is a bigger increase compared to commercial in the US. So question regarding wind and solar, so some questions you can think about. Number one, what materials are used to make wind turbine and PV cells? So what are the raw materials we use to make these materials? And then are these materials renewable? And then the process for making these materials, are they green? Okay. And then if we have a lot of people install wind and solar, how about the price? Can we still have a low cost, low price? So that's something you can think about when you have time. So back to the first slide I have here, you have the house, you bring the resources to support your life, and then we discharge wastewater and solid waste. So this is our daily life so far. So what if we remove these 2 waste? Okay, we don't have wastewater, we don't have solid waste. I mean, we cannot go without. We will definitely generate waste, right? But what if we give them different names? So instead of wastewater, can we say this is used water? Like you have used clothes, can we say this is used water? Okay. Or solid materials, can we just say this is used materials? Now with assistance of solar and wind, we can generate electricity, we can generate clean water, we can produce fuels and chemicals, fertilizers. Okay. And then we can use this to support commercial development, industry, and agriculture, and of course, individual household, residential. So overall, if we have this sustainable design, we can have this circular economy. So in this economy, you don't see waste. So everything is being used, reused, and cycled. So with that, I'm going to conclude my presentation. Any questions?
I got a question. I talked to an engineer, and I don't take everything for gospel, so you're an expert, so I'd like to know if this is true or not. He said that with the solar panels that people are putting on their houses today, they are very effective. They're going to do tremendous things for energy. He said, but what people don't realize is there was 1 or 2 chemicals, and I forget exactly what they are, that are so embedded in these panels that when they reach their design life of 20, 30, 35, 40 years, we're going to have an epidemic of trying to get rid of these 2 chemicals that is extremely costly in trying to get out of the panels. So he said it's a short fix now, but it could be an environmental disaster later on. It's so cost effective to get those out. I'm just wondering, has anything come across that by you? Is that fact or fiction?
I don't know. I'm not expert on solar, so I really don't know what these two chemicals are. But like the questions I posed to you, you have to think from the beginning to end, the whole life cycle. What do you use to make solar panels? And then once they reach the lifetime, how do you dispose and then discard these materials? So we have to think of a life cycle for basically everything.
Right.
The whole life cycle analysis in addition to the whole techno-economic analysis. So yeah, that's right. I mean, we have to be proactive, and so far we have been reactive. So if there is contamination, we decontaminate, we clean up, but oftentimes we're not proactive enough. So that's very good, your friends all.
I'm going to research that. I want to know what chemicals they are. And he said, Brian, you just can't throw them into the environment. You can't just put it in a landfill. And they have to be removed. And the process is going to be a nightmare. So he said, it's something that's coming down the pike.
Yeah, I'm sure lots of chemicals are used in making this wind turbine and PV cells. And again, right now we just use them. They are useful, but we don't think about consequences later. Yeah, so that's like I said, have we learned the lessons, The chemists are very smart. They can synthesize lots of chemicals and then pesticide, herbicide, drugs. I mean, they are beneficial right now, nowadays, but then what happens later? And also the price. So if the consumption of solar and wind increases, what about the price? So I think that happens with some rare earth element, but they are used in electronics, and then there's a shortage of this element, and then the price just shoot up. So all of this stuff.
Can you just tell us more about the nanoparticles? Because can you explain how are they different from other like organic molecules that might be harmful in some other way? What is it specifically about the nanoparticles that make them dangerous or biologically active in some way?
Okay, yeah. So the question was why nanoparticles are so dangerous compared to the bulk chemicals. Now, nanoparticles, basically, there are some that are metal, like we talked about titanium, zinc, silver. They are metal oxide, they are metals. And then some are carbon, like you have carbon nanotubes. They're carbon, they're not metals. I think the major reason for their reactivity is the size. Like I said, nanometer is just too small. Okay, so they can penetrate the cell membrane, go into the cells, and they can disrupt the whole structure of the cells, and the cells will die. The microbes will die. And then some, they are photoactive, like titanium dioxide and zinc oxide. They are photoactive. Once they are exposed to light, they can produce like reactive oxygen species. So these are kind of like these bad species in a human body. We have to use like antioxidant to destroy these chemicals. So there are lots of negative effects we're still studying, like how they can affect microbes, how they can affect like human cell types. The size is a critical matter, and a lot of nanomaterials or particles sold by different suppliers, they are either coated or have different functional groups added. So they are good for certain reactions, for certain purposes, but again, you have these chemical groups attached to nanoparticles. In some cases, the impact could be even worse.
Just about this nano, in this case, I understood that basically the destruction of it nowadays possible would be based on very high temperatures.
You mean for nano?
When you presented the recycling or possible recycling or elimination of nanoparticles. So, but in this process, first of all, the material would have to be in one place and be handled. In the meantime, all of that goes in some way into the atmosphere on the way or on the process. So is there any way that we can maintain it?
You mean
under
nanomaterials?
control, given the size and given...
So you're talking about nanomaterials, right? How can we...
Yeah, if there is any way to really keep it contained.
Keep it contained. Well, I would say it is difficult. Now, number one, the size, they are so small.
Yeah.
So they are small, they don't easily precipitate or settle. So they will remain in suspension. okay, because of small size. And number two is these nanoparticles like silver and zinc, they can dissolve in water and form ions, silver ions and zinc ions. Now we've been using silver for a long time for antimicrobial purposes. So their goal is to kill or inactivate microbes. Now we are using them in lots of products, and then the products will be released to the environment, and you have the silver nanoparticles released in the environment. No, it is not that easy. Yeah, no. Yeah, size and also their solubility, reactivity.
I don't recall you saying anything specifically about plastics, microparticles. I recently read something by somebody at Fredonia, 2017 study of plastic microparticles in drinking water and bottled water. And the things are everywhere.
Yeah, you're right. So plastics or microplastics, I mean, it is a big concern right now. Especially, I think there are some videos, movies showing you have the plastics piled up in one part of the ocean. I forgot the name. So you have this huge junk piled up at that place. So you have plastics detected in fish and then sea animals and whatever. Yeah, I mean, that is a huge, huge issue. Yeah. So right now, I think the topic we are discussing is, can we design plastics that are biodegradable? So the plastic we use, majority, they are not biodegradable. So use them and you throw them to the environment and then just stay there. They are not degradable. So can we have plastics have the same function, but then they can degrade over time in nature? Several years ago, I think when I started my career, so there is a company, I think it's called Metabolomics, something. So that company, their focus is to design or produce plastics, it's called bioplastics, that are biodegradable. So that is using microbes in a fermentation process, using genetically engineered microbes to produce plastics that are degradable in the nature. Again, technically it is feasible. Economically, I don't know how that can compete with plastics from fossil fuels.
A lot of it's coming out in the wash, so if it's biodegradable, if you wash it, it can basically all go away. These microplastics, what I've heard is like polar tack and fleece. When you wash it, that's where a lot of the microplastics are coming.
Released.
Yeah, they're degrading in the wash cycle and going out through the water that way.
But it's not completely disappear. I mean,
No.
yeah, so it goes to these micro-sized particles of plastics, and then they could pose even more danger to the environment for the size.
We are slightly over time, but I know. But thank you, Dr. Liang. That's wonderful and very, very